The impossible machine. The conference room at Republic Aviation's Farmingdale, New York facility fell silent. It was the spring of 1940, and Alexander Kartveli had just unveiled his proposal for America's next fighter aircraft. The engineers and military officials gathered around the table stared at the blueprints with expressions ranging from confusion to outright disbelief. "You want to build a fighter that weighs how much?" Colonel Benjamin Kelsey of the U.S. Army Air Corps finally asked, breaking the uncomfortable silence. 12,000 pounds, Kartveli replied in his thick Georgian accent, not flinching. Empty weight, fully loaded, closer to 15,000. For context, the superlative Supermarine Spitfire, Britain's legendary defender, weighed barely 5,000 pounds empty. The Messerschmitt Bf 109, Germany's frontline fighter, came in at just over 4,000 pounds. Kartveli was proposing a fighter that would be 3 times heavier than its contemporaries. That's not a fighter, that's a flying bathtub. What they didn't understand, what virtually nobody in that room could comprehend at that moment, was that Alexander Kartveli wasn't designing a conventional fighter at all. He was engineering a solution to a problem that the aviation world hadn't fully recognized yet. The war would be won or lost in the thin, frigid air above 30,000 feet, where existing fighters gasped for oxygen and their engines wheezed like dying men. The aircraft that emerged from Kartveli's ridiculous design would become the Republic P-47 Thunderbolt, and it would revolutionize aerial warfare. Its secret wasn't just in its massive Pratt & Whitney R2800 engine and its 850 caliber machine guns. The true genius lay in a complex system of tubes, turbines, and intercoolers that would allow this 7-ton monster to climb higher than any Axis fighter could follow and still have enough power to fight when it got there.
The problem nobody saw coming. The altitude imperative. In 1940, most military aviation strategists were still fighting the last war. The Spanish Civil War and the early campaigns of World War II had suggested that air combat would primarily occur between 15,000 and 20,000 feet. Fighter designs reflected this assumption. The early model Spitfire Mk1 had a service ceiling of around 31,000 feet, but performed optimally below 20,000 feet. The Bf 109E could theoretically reach 34,000 feet, but its combat effectiveness deteriorated sharply above 25,000 feet. But strategic bombing doctrine was evolving rapidly, and with it, the altitude requirements for escort fighters. The Boeing B-17 Flying Fortress, America's primary strategic bomber, was designed to operate at altitudes between 25,000 and 30,000 feet. The theory was simple: fly high enough and enemy fighters couldn't reach you. The problem, of course, was that enemy fighters could reach those altitudes. They just couldn't fight effectively when they got there. The physics of high-altitude flight presented a cascade of interconnected challenges. As an aircraft climbs, atmospheric pressure decreases exponentially. At 30,000 feet, the air pressure is roughly 1/3 of sea level pressure. For a piston engine, which relies on air intake to function, this is catastrophic. An engine that produces 1,200 horsepower at sea level might generate only 400 horsepower at 30,000 feet without some form of forced induction. Traditional superchargers, mechanically driven compressors that forced more air into the engine, helped, but they had significant limitations. A mechanically driven supercharger was parasitic. It stole power from the very engine it was supposed to enhance. At high altitudes, a mechanically driven supercharger might consume 200 to 300 horsepower just to operate, leaving precious little for actual propulsion. Enter Alexander Kartveli. Alexander Kartveli was not a man who accepted limitations gracefully. Born in Tiflis, Georgia, then part of the Russian Empire, in 1896, he had studied engineering in Paris before immigrating to the United States in 1927. He joined Republic Aviation's predecessor company in 1931 and quickly established himself as a brilliant, if unconventional, designer. By 1940, Kartveli had already designed the P-43 Lancer, Republic's first attempt at a modern fighter. The P-43 was notable for being one of the first American fighters with a turbocharged engine, but it was plagued with problems and never saw significant combat. The experience, however, taught Kartveli invaluable lessons about high-altitude design. When the Army Air Corps issued a request for proposals for a new fighter in 1940, the specifications were demanding: a top speed of at least 400 miles per hour, heavy armament, self-sealing fuel tanks, armor protection for the pilot, and, critically, the ability to operate effectively at high altitudes. The military was finally beginning to understand what strategic bombing would require. Kartveli's response to these requirements was characteristically bold. Rather than try to incrementally improve existing designs, he started from first principles. If high-altitude performance was paramount, then every aspect of the design needed to serve that goal, even if it meant breaking every convention of fighter design. The turbo-supercharger, the heart of the solution. The key to Kartveli's design was the General Electric turbo-supercharger, a technology that had been in development since the 1920s but had never been successfully integrated into a frontline fighter. Unlike a mechanically driven supercharger driven by the engine's crankshaft, a turbo-supercharger, or turbo-supercharger as it was then called, was powered by the engine's exhaust gases. The concept was elegantly simple. Exhaust gases that would otherwise be wasted spun a turbine, which in turn drove a compressor that forced pressurized air into the engine. Because it didn't draw power directly from the crankshaft, it was far more efficient at high altitudes. The General Electric Type B-Series turbo-supercharger that Kartveli planned to use could maintain sea-level pressure in the engine's intake manifold up to approximately 30,000 feet. This meant that the Pratt & Whitney R2800 Double Wasp, engine already a powerhouse at 2,000 horsepower at sea level, could maintain near maximum power output at altitudes where other fighters' engines were gasping for air. But integrating a turbo-supercharger into a fighter aircraft was monumentally difficult. The turbo-supercharger itself was large and heavy. The turbine, spinning at over 20,000 RPM and heated by exhaust gases exceeding 1,600 degrees Fahrenheit, required careful placement and extensive heat shielding. The compressed air coming out of the compressor was also extremely hot, too hot to feed directly into the engine without causing detonation. This required an intercooler, adding yet more weight and complexity. Make it work. I don't care how big it gets. Republic Aviation's engineers presented Kartveli with study after study showing that integrating a turbo-supercharger system into a fighter airframe while maintaining reasonable dimensions was extremely difficult, perhaps impossible. The ducting alone, the system of tubes that would carry exhaust gases to the turbine and compressed air to the engine, would need to run the length of the fuselage. Kartveli's response became legendary within Republic Aviation. Make it work. I don't care how big it gets. This single decision, prioritizing performance over conventional size and weight limitations, defined everything that followed. The P-47 would be built around its turbo-supercharger system, not the other way around. The General Electric turbo-supercharger was installed in the rear fuselage, behind the pilot. Exhaust gases from the massive R2800 engine were collected by manifolds and ducted back through pipes running along either side of the cockpit. These pipes, each several inches in diameter, had to be carefully insulated to prevent them from turning the cockpit into an oven. The exhaust gases spun the turbine, which drove the compressor on the other side of the same shaft. The compressed air then faced another journey. It exited the compressor at temperatures exceeding 300 degrees Fahrenheit and had to be cooled before entering the engine. Kartveli's solution was an intercooler mounted in the lower forward fuselage, where ram air could flow through it during flight. This intercooler was essentially a radiator for air. Compressed air from the turbo-supercharger flowed through tubes while outside air flowed over them, removing heat. After cooling, the air made yet another journey through ducting that ran forward to the engine's intake manifold. The entire system, turbine, compressor, ducting, intercooler, controls, and wastegates, added over 1,500 pounds to the aircraft's weight.
Building the beast. The prototype takes shape. By late 1940, Republic Aviation's factory floor was dominated by a massive assemblage of metal that bore little resemblance to contemporary fighters. Where the Spitfire and Bf-109 were slender and graceful, the P-47 prototype was broad and muscular. Its fuselage was enormous, nearly 4 feet in diameter at its widest point, necessary to accommodate the R2800 engine, ducting, and turbo-supercharger. The Pratt & Whitney R2800 Double Wasp was itself a marvel of engineering. This 18-cylinder, twin-row radial engine displaced 2,800 cubic inches, hence its designation, and produced 2,000 horsepower. It was one of the most powerful aircraft engines in the world, and it was reliable, a crucial factor that would prove decisive in combat. Mounting this massive engine required a substantial engine mount and a large-diameter cowling. The cowling was carefully designed to manage airflow, with adjustable gill flaps that could be opened or closed to regulate engine cooling. This attention to engine cooling would prove critical. The R2800 generated tremendous heat, and managing that heat at high altitudes, where cooling air was thin, required sophisticated engineering. Behind the engine in cockpit, the fuselage swelled even larger to accommodate the turbo-supercharger system. The turbine sat in a compartment that required special heat-resistant materials and careful design to prevent fire risk. The wastegate, a controllable valve that could divert exhaust gases around the turbine, was crucial for regulating boost pressure and protecting the engine from overboosting. The wing, strength through size. The wings of the P-47 were another area where Kartveli's bigger is better philosophy manifested. With a span of just over 40 feet and an area of 300 square feet, the P-47's wings were substantially larger than those of comparable fighters. This wasn't just to support the aircraft's weight, though that was certainly a factor. Large wings provided two critical advantages. First, they reduced wing loading, the ratio of weight to wing area. Despite the P-47's massive weight, its wing loading was actually comparable to lighter fighters because of its large wing area. This translated to better turning performance than engineers initially expected from such a heavy aircraft. Second, the large wings provided ample room for fuel and armament. Each wing contained fuel tanks with a total capacity of 305 gallons internally, plus provisions for external drop tanks. The armament was equally impressive. 4.5 caliber M2 Browning machine guns in each wing for a total of 8 guns. Each gun was supplied with 425 rounds of ammunition, more than any contemporary fighter. The wing design also incorporated lessons learned from European combat. The P-47's wings were exceptionally strong, built to withstand high G loads and, critically, the stresses of high-speed dives.
This strength would prove invaluable in combat, where P-47 pilots would regularly push their aircraft to speeds exceeding 500 miles per hour in dives, speeds at which lighter fighters often experienced structural failures. Cockpit and controls. The P-47's cockpit was roomier than that of most fighters, a consequence of the aircraft's overall size. This was welcome to pilots, but also reflected careful ergonomic design. Kartveli understood that pilots operating at high altitudes for extended periods needed a comfortable workspace. The cockpit featured a sophisticated heating system, essential for survival at 40,000 feet, where temperatures could plunge to minus 60 degrees Fahrenheit. The heating system drew warm air from around the engine and ducted it to the cockpit, though pilots reported it was often inadequate in extreme cold. The instrument panel was comprehensive, featuring all standard flight instruments plus specialized gauges for the turbo-supercharger system. Pilots needed to monitor turbine RPM, manifold pressure, and intercooler temperature. Managing the turbo-supercharger required skill. Too much boost could destroy the engine, while too little negated the system's advantages. Perhaps the most innovative cockpit feature was the turbo-supercharger control itself. Unlike earlier installations that used complex manual controls, the P-47 system featured an automatic regulator that adjusted turbine speed to maintain desired manifold pressure as altitude changed. Pilots could override this system if needed, but the automatic regulator made high-altitude operations far less demanding. Behind the pilot seat was armor plating, thick steel designed to protect from fire from the rear. The windscreen incorporated bulletproof glass. These protective features added weight but reflected hard lessons from European combat. Fighters needed to protect their pilots. The landing gear challenge. The P-47's weight created a significant challenge for landing gear design. The main landing gear had to support over 7 tons of aircraft, including fuel and ammunition, and withstand the impacts of carrier-style landings on rough forward airfields. Kartveli's solution was robust if inelegant. The main landing gear was extraordinarily strong, with large wheels and heavy-duty oleos, shock absorbers, to cushion landing impacts. The gear retracted inward into the wing, a design choice that kept it close to the fuselage centerline for better structural efficiency. The large wheels and sturdy gear gave the P-47 excellent ground handling characteristics. Unlike some contemporary fighters that were notoriously difficult to control on the ground, the P-47 was stable during takeoff and landing, a significant advantage for the less experienced pilots that would eventually fly it. First flight, May 6, 1941. On May 6, 1941, Republic test pilot Lowry Brabham climbed into the cockpit of the XP-47B prototype for its first flight. The massive fighter, painted in bare metal with minimal markings, sat on Republic's runway like a silver giant among pygmies. Brabham advanced the throttle, and the R-2800 roared into action. The sound was distinctive, deeper, and more powerful than the inline engines of most contemporary fighters. As the P-47 accelerated down the runway, observers noted how much runway it consumed before lifting off. This would become a characteristic of the type. The P-47 needed a long takeoff run, especially when fully loaded. But once airborne, the prototype revealed its true nature. Brabham climbed steadily, and the big fighter proved surprisingly responsive. The controls were heavy compared to lighter fighters, a consequence of the P-47's size and weight, but they were well harmonized and precise. The flight lasted only a few minutes, enough to verify that all systems were functioning and the aircraft was controllable. When Brabham landed and shut down the engine, his report was guardedly positive. The airplane flew. What remained to be seen was whether it could fulfill Kartveli's ambitious performance promises.
Testing the theory. Early flight tests, discovering the potential. The initial flight test program for the XP-47B revealed both promising capabilities and significant challenges. In level flight at low to medium altitudes, the prototype was fast, but not spectacularly so. Its top speed at sea level was around 360 miles per hour, Respectable, but not exceptional for 1941. The real revelation came when test pilots began exploring the aircraft's high-altitude performance. As the P-47 climbed above 25,000 feet, altitudes where most fighters began to struggle, the turbo-supercharger system proved its worth. While the R-2800 engine in other installations would have been gasping for air, the turbo-supercharger maintained manifold pressure, keeping power output high. Lowry-Brabham's flight test reports from December 1941, preserved in the National Museum of the USAF archives, document the growing excitement among test pilots. At 30,000 feet, the P-47 was still accelerating briskly, its engine producing nearly full power. At 35,000 feet, it maintained excellent performance. By the time the prototype reached 38,000 feet, it was operating in air so thin that pilots needed pressurized oxygen systems just to remain conscious, yet the P-47's engine was still running smoothly. The service ceiling, the altitude at which the aircraft could still climb at 100 feet per minute, was eventually established at approximately 42,000 feet, though this varied slightly with different models and configurations. This was extraordinary performance. For comparison, the Spitfire Mark V, Britain's frontline fighter in 1941, had a service ceiling of about 37,000 feet. The Bf-109F, Germany's best fighter at the time, topped out around 39,000 feet. The P-47 could climb higher than any operational fighter on either side. The dive test revelation. Another surprising discovery during early flight tests concerned the P-47's diving performance. The aircraft's weight, which seemed like such a liability, became an asset in dives. Physics dictated that a heavier object accelerated faster in a dive, and the P-47 proved this dramatically. Test pilots found that the P-47 could exceed 500 miles per hour in a dive, velocities where aerodynamic compression effects became significant. The strong wing structure that Kartveli had insisted upon proved essential. Lighter fighters often experienced control issues or structural problems at these speeds, but the P-47 remained stable and controllable. This diving capability would become tactically significant. In combat, a P-47 pilot who found himself in trouble could push the nose down and dive away from virtually any Axis fighter. German and Japanese fighters simply couldn't follow. If they tried, they risked structural failure. This gave P-47 pilots a reliable escape option, something that couldn't be said for all fighter types. Problems emerge. Not everything about the early P-47 was positive. The aircraft had several significant problems that needed resolution before it could enter combat service. The most serious issue involved the turbo-supercharger system itself. The complex ducting and high temperatures created maintenance headaches. Exhaust leaks were common and could fill the cockpit with noxious fumes or even cause fires. The intercooler proved prone to icing at high altitudes, where moisture in the compressed air would freeze and block airflow. The turbine itself was temperamental. Spinning at over 20,000 RPM and subjected to enormous thermal stresses, turbine wheels sometimes failed catastrophically, sending turbine blades through the fuselage like shrapnel. Engineers had to develop improved turbine materials and better bearing systems to prevent these failures. Engine cooling presented another challenge. The R-2800 generated prodigious heat, and managing that heat, especially during ground operations and climbouts, required careful attention to cowl flap settings. Overheating could cause engine damage or failure, a potentially fatal problem over enemy territory. The P-47's weight created operational constraints. Takeoff runs were long, requiring substantial runway length. Fully loaded, a P-47 might need 5,000 feet of runway, a requirement that limited which airfields could operate the type. In combat zones, this would prove a significant limitation. Range was another concern.
Despite its large internal fuel capacity, the P-47's thirsty R-2800 engine consumed fuel rapidly. Early models had a combat radius of only about 200 miles, inadequate for escort missions deep into Germany. This problem would require significant attention. Production begins. Despite these challenges, the Army Air Forces recognized the P-47's potential and ordered the aircraft into production. In December 1941, just weeks after Pearl Harbor brought the United States into World War II, Republic Aviation received contracts for hundreds of P-47s. The production program faced immediate challenges. The P-47 was complex and expensive to manufacture. Its large size required substantial materials. The turbo-supercharger system involved precision manufacturing of components that pushed the limits of American industrial capability. Republic Aviation's Farmington, New York factory underwent massive expansion. New assembly lines were established, and thousands of workers were hired. Eventually, a second production facility was opened in Evansville, Indiana, which would produce thousands of additional P-47s. The production P-47B differed in various details from the ex-P-47B prototype, incorporating lessons from flight testing. The turbo-supercharger system was refined, with improved ducting and better intercooler design. The cockpit received improvements, and provisions were added for external drop tanks to extend range. By late 1942, P-47s were rolling off production lines at increasing rates. The massive fighters were ferried to training bases where pilots began converting to the type. Many pilots, accustomed to lighter fighters, were initially dismayed by the P-47's size and weight. The aircraft was nicknamed Jug, short for Juggernaut, by pilots, who weren't sure the nickname was entirely complimentary.
Combat debut. Arrival in England. The first P-47s arrived in England in December 1942, assigned to the 4th and 56th Fighter Groups of the 8th Fighter Command. These units, tasked with escorting American bombers on raids over occupied Europe, had been flying Spitfires borrowed from the RAF. The transition to the P-47 was not universally welcomed. British pilots and ground crews, seeing the P-47 for the first time, were incredulous. The aircraft dwarfed the Spitfire. Standing next to both types, the difference was almost comical. The graceful, delicate Spitfire looked like a sports car beside the P-47's heavy truck. RAF Boscombe Down, Britain's premier aircraft testing facility, conducted evaluation flights of the P-47C in 1943. Their reports, preserved in British Air Ministry archives, were diplomatically worded but expressed significant skepticism. The P-47 was heavily built, quite large, and showed moderate maneuverability at low altitudes. British evaluators concluded that while the P-47 had impressive high-altitude performance, they preferred their Spitfires for the combat conditions over Europe. American pilots were equally dubious. Accustomed to training in lighter aircraft, they found the P-47 heavy on the controls and ponderous compared to the Spitfire. Its rate of roll was slower, and it couldn't turn as tightly at low speeds. In mock dogfights against Spitfires, P-47s often appeared disadvantaged. The first missions. On March 10, 1943, the 4th Fighter Group flew the P-47's first combat mission, a fighter sweep over France. The mission was uneventful. No enemy aircraft were encountered, but the P-47s returned safely, proving they could operate over enemy territory. The first combat engagement came on April 15, 1943. Major Don Blakesley, leading a flight of 4th Fighter Group P-47s, encountered a formation of Focke-Wulf FW-190S near the French coast. The ensuing engagement was brief and inconclusive, but it provided valuable lessons. The FW-190 was Germany's best fighter at low to medium altitudes, and in a low-altitude turning fight, it could outmaneuver a P-47. However, American pilots quickly discovered that the P-47's strengths lay elsewhere.
In a dive, the P-47 could accelerate away from an FW-190. At high altitudes, above 25,000 feet, the P-47's turbo-supercharged engine gave it a decisive power advantage. Tactical evolution, playing to strengths. The early combat experiences led to rapid tactical evolution. Squadron and group commanders, often in consultation with experienced pilots, developed tactics that exploited the P-47's advantages while minimizing its weaknesses. The fundamental principle was simple: fight on your terms, not the enemy's. P-47 pilots were instructed to maintain high altitude and high speed. The preferred attack method became the bounce, diving from high altitude onto enemy fighters below, making a high-speed attack pass, and then zooming back up to altitude using the energy gained in the dive. This vertical style of combat, boom and zoom as it came to be called, played perfectly to the P-47's strengths. The aircraft's excellent high-altitude performance meant P-47 pilots could position themselves above enemy formations. The powerful dive capability allowed devastating attack passes. The zoom climb that followed took the P-47 back to safe altitude before enemy fighters could respond effectively. Conversely, P-47 pilots learned to avoid sustained turning dogfights, especially at low altitudes where the aircraft's weight became a severe liability. If a P-47 pilot found himself in a slow-speed, low-altitude turning fight with a BF-109 or FW-190, he was in trouble. The solution was to use the P-47's superior dive performance to disengage, gain speed and altitude, and reset the engagement on favorable terms. The 56th Fighter Group, Zemke's Wolfpack. No unit better exemplified the P-47's potential than the 56th Fighter Group, commanded by Colonel Hubert Zemke. Zemke, a brilliant tactician and natural leader, embraced the P-47 and developed doctrine that maximized its capabilities. Zemke insisted on rigorous training in high-altitude tactics. His pilots practiced diving attacks, zoom climbs, and high-speed maneuvering. They learned to work together, with wingmen protecting each other and flights coordinating attacks. The 56th Fighter Group became known as Zemke's Wolfpack, and their combat record soon reflected their tactical sophistication. The Wolfpack's first significant victory came on June 26, 1943, when they claimed 8 German fighters destroyed without loss. This was a turning point, proof that properly employed, the P-47 could dominate the Luftwaffe. Throughout the summer and fall of 1943, the 56th Fighter Group's victory tallies mounted. Pilots like Robert S. Johnson, Francis Gabby Gabreski, and Walker Bud Mahurin became aces, each developing personal variations on the basic boom and zoom tactics. The altitude advantage proved decisive. Combat records from 8th Fighter Command mission reports through 1943-1945 demonstrate how consistently P-47 pilots exploited their altitude advantage. Typical engagement patterns show P-47s patrolling at 28,000 to 32,000 feet, positioned to intercept German fighters attacking bomber formations below. German pilots flying BF-109Gs and FW-190As typically attacked bomber formations from head-on or from below, tactics designed to minimize exposure to bomber defensive fire. These attacks brought them into the P-47's preferred engagement envelope. Diving from above with tremendous speed, P-47s could make devastating passes on climbing or maneuvering German fighters. Luftwaffe pilot interrogation records from 1945, collected by the U.S. Strategic Bombing Survey, revealed German pilots' respect and frustration regarding the P-47. One captured pilot stated, "The Thunderbolt could always climb above us. When we attacked the bombers, the Thunderbolts fell on us from above very fast. If we turned to fight, they would not turn with us, but would climb back up and then dive again." This quote captures the essential tactical reality. The P-47's high-altitude capability gave American pilots control over the engagement. They could choose when and how to fight, dictating the terms of combat. Robert Johnson's story, Durability Under Fire. The P-47's strength and durability became legendary through incidents like the one involving Captain Robert Johnson on June 26, 1943. Johnson, flying a P-47C with the 56th Fighter Group, was attacked by German fighters during a bomber escort mission over France. An FW-190, piloted by an experienced German fighter pilot, later identified as possibly Egon Meyer, a German Luftwaffe ace, attacked Johnson's P-47. Cannon shells struck Johnson's aircraft multiple times, damaging the engine, shredding control surfaces, and shattering the cockpit canopy. Johnson himself was wounded by shell fragments. Unable to defend himself or maneuver effectively, Johnson expected his aircraft to break apart or catch fire. Instead, the massive P-47 absorbed tremendous punishment and kept flying. Johnson nursed the crippled fighter across the English Channel and made an emergency landing at an RAF base on the English coast. Ground crews counted over 200 bullet and cannon shell holes in Johnson's P-47. The engine had been struck multiple times but continued running. Control cables were severed, yet redundant systems kept the aircraft controllable. The airframe structure, though damaged, maintained integrity. This incident and others like it established the P-47's reputation for toughness. Pilots knew their aircraft could take punishment and bring them home, a confidence that translated to aggressive combat tactics.
Technical Deep Dive: the turbo-supercharger system. Understanding the technology. To fully appreciate the P-47's high-altitude capability, one must understand the turbo-supercharger system in detail. This system represented the cutting edge of 1940s aviation technology, and its successful integration into the P-47 was a remarkable engineering achievement. The General Electric Type B Series turbo-supercharger consisted of several key components. The turbine wheel, manufactured from heat-resistant alloy steel, was approximately 10 inches in diameter and featured curved blades designed to extract maximum energy from exhaust gases. This wheel was mounted on a shaft with precision bearings that allowed it to spin at over 21,000 RPM while subjected to temperatures exceeding 1,500 degrees Fahrenheit. On the opposite end of the same shaft was the compressor wheel, slightly larger in diameter, with blades designed to compress intake air efficiently. As the turbine spun, it drove the compressor, which drew in ambient air and compressed it to higher pressure. The system's efficiency depended on several critical factors. First, the turbine had to extract sufficient energy from the exhaust gases to drive the compressor without creating excessive back pressure that would impede the engine's exhaust flow. Second, the compressor had to provide adequate airflow at the required pressure without consuming more power than the turbine could supply. The ducting challenge. The physical layout of the turbo-supercharger system in the P-47 was extraordinarily complex. Exhaust gases from the R2800 engine's 18 cylinders had to be collected, routed to the turbine, and then expelled overboard. Compressed air from the compressor had to be cooled, then routed to the engine's intake manifold. The exhaust ducting consisted of large-diameter steel tubes that ran along either side of the cockpit, converging at the turbo-supercharger unit in the rear fuselage. These tubes were double-walled with an air gap for insulation, yet they still radiated significant heat. In flight, the cockpit's temperature varied wildly depending on power settings and ambient conditions, sometimes unbearably hot during climbouts, then frigidly cold at high altitude. From the turbulent supercharger's turbine, exhaust gases were expelled through a tailpipe that exited under the rear fuselage. The wastegate, a controllable valve that could divert exhaust gases around the turbine, was positioned in this ducting. By opening the wastegate, pilots could reduce boost pressure when full power wasn't needed, protecting the engine from overboosting and improving fuel efficiency. The compressed air path was equally complex. Air exited the compressor at high pressure and temperature, often 300 to 400 degrees Fahrenheit. This superheated air flowed forward through ducting to the intercooler, located in the belly of the aircraft beneath the engine. The intercooler was essentially an air-to-air heat exchanger. Compressed air from the turbo-supercharger flowed through a matrix of tubes, while ram air outside, accelerated by the aircraft's forward motion, flowed across these tubes. Heat transferred from the compressed air to the ram air, reducing the compressed air's temperature. This cooling was absolutely essential for several reasons. Hot air is less dense than cool air. So cooling the compressed air increased its oxygen content per unit volume. More oxygen meant better combustion and more power. Additionally, excessively hot intake air could cause pre-ignition or detonation in the engine cylinders, potentially catastrophic conditions that could destroy an engine in seconds. The intercooler's effectiveness varied with flight conditions. At high speeds, ram airflow was excellent, and the intercooler worked well. During slow flight or ground operations, airflow was reduced and cooling efficiency decreased. This was one reason P-47s needed careful management during takeoff and climbouts. Power had to be moderated until sufficient airspeed was achieved for effective intercooling. From the intercooler, cooled compressed air flowed through additional ducting to the engine's intake manifold. This final section of ducting incorporated the carburetor, where fuel was mixed with the compressed air before entering the cylinders. Control systems, managing the beast. Operating the P-47's turbo-supercharger system required skill and understanding. The pilot had several controls and numerous gauges to monitor. The primary control was the throttle, which governed engine RPM and power output in the conventional manner. However, the turbo-supercharger added layers of complexity. Advancing the throttle increased fuel flow and engine speed, which increased exhaust gas flow, which spun the turbine faster, which increased boost pressure, which increased power output, a feedback loop that required careful management. Manifold pressure, the pressure of intake air entering the engine, was critical. Too little manifold pressure and the engine produced insufficient power. Too much and the engine could suffer catastrophic damage from detonation. Pilots monitored manifold pressure constantly, adjusting throttle settings to maintain desired pressure. The turbo-supercharger control, often called the turbo lever, allowed pilots to adjust the wastegate position, controlling how much exhaust gas bypassed the turbine. In automatic mode, a regulator adjusted the wastegate to maintain constant manifold pressure as altitude changed. In manual mode, pilots could override this, though doing so required constant attention to prevent overboosting. The turbine RPM gauge showed how fast the turbo-supercharger was spinning. Excessive turbine speed could cause mechanical failure, so pilots had to monitor this carefully. The intercooler temperature gauge indicated compressed air temperature. If this climbed too high, it suggested intercooler icing or insufficient ram airflow. Managing all these parameters while flying combat missions, navigating, communicating via radio, watching for enemy fighters, and coordinating with other aircraft required exceptional skill. P-47 pilots underwent extensive training specifically on turbo-supercharger operations before being cleared for combat.
Reliability issues and solutions. Early P-47s experienced numerous turbo-supercharger-related failures. The extreme operating conditions, high rotational speeds, enormous thermal stresses, and constant vibration pushed materials and design to their limits. Turbine wheel failures were among the most dangerous problems. A turbine wheel disintegrating at 21,000 RPM released fragments with tremendous energy. These fragments could penetrate the fuselage, sever control cables, or damage other critical systems. Several early P-47s were lost to turbine failures, and engineers worked urgently to address the problem. The solution involved multiple improvements. General Electric developed new alloy formulations with better high-temperature strength and fatigue resistance. Manufacturing processes were refined to eliminate microscopic flaws that could propagate into cracks under thermal cycling. Inspection procedures became more rigorous, with each turbine wheel subjected to X-ray examination and magnetic particle testing to detect hidden defects. Bearing failures were another persistent issue. The turbo-supercharger shaft operated at extreme speeds while subjected to thermal expansion and contraction. The bearings had to accommodate these conditions while maintaining precise clearances. Early bearings sometimes seized or wore rapidly, leading to turbine failures. Engineers addressed this through improved bearing materials, better lubrication systems, and more robust bearing designs. The lubrication system for the turbo-supercharger was separate from the engine's main oil system, using its own oil supply and scavenge pumps. This isolation prevented contamination and allowed use of lubricants specifically formulated for high-temperature operation. Exhaust leaks plagued early P-47s. The exhaust ducting operated at temperatures that caused thermal expansion and contraction with every flight. Joints and connections had to accommodate this movement while maintaining gas-tight seals. Early seal designs often failed, allowing hot exhaust gases to escape into the fuselage. The consequences ranged from merely unpleasant, cockpit fumes that made pilots nauseous, to potentially catastrophic. Exhaust gases escaping near fuel lines or hydraulic systems could cause fires. Republic Aviation and its suppliers developed improved joint designs using flexible couplings and high-temperature gasket materials that better accommodated thermal cycling. Intercooler icing was a particularly insidious problem. At high altitudes where temperatures were far below freezing, moisture in the compressed air could freeze when passing through the intercooler. Ice accumulation restricted airflow, reducing intercooler effectiveness and eventually blocking it completely. This caused intake air temperatures to soar, leading to detonation and possible engine failure. The solution involved several approaches. Drainage systems were improved to remove condensed moisture before it could freeze. Anti-icing fluid injection systems were developed, introducing methanol water mixture into the compressed airstream. The anti-icing fluid lowered the freezing point of any moisture present, preventing ice formation. Additionally, pilots were trained to recognize symptoms of intercooler icing and take corrective action, including descending to warmer altitudes or adjusting power settings. Comparative performance analysis. To understand just how significant the P-47's high-altitude capability was, it's useful to compare its performance against contemporary fighters using data from technical reports and performance trials. At 30,000 feet, a standard combat altitude for bomber escort missions, the P-47D could maintain a top speed of approximately 428 miles per hour. The Spitfire Mark IX, Britain's improved high-altitude fighter introduced in 1942, could achieve about 408 miles per hour at the same altitude. The Bf-109 G6, Germany's primary fighter in 1943-44, managed approximately 386 miles per hour at 30,000 feet. The FW-190A8 was slightly slower, around 375 miles per hour at that altitude. These numbers revealed the P-47's advantage. At high altitude, it was simply faster than anything the Germans could field. This speed advantage, combined with superior high-altitude power, gave P-47 pilots tactical options unavailable to their opponents. Rate of climb comparisons are equally revealing. From 25,000 to 30,000 feet, a critical performance band for intercepting bomber formations, the P-47D could climb at approximately 2,000 feet per minute under combat power. The Spitfire Mark IX managed about 1,800 feet per minute, and the Bf-109 G6 roughly 1,400 feet per minute in this altitude band. This climb rate advantage meant P-47 formations could rapidly reposition vertically, climbing above enemy fighters or diving to bomber escort altitude and then zooming back up faster than German fighters could follow. Perhaps most telling were service ceiling comparisons. The P-47D's service ceiling of 42,000 feet gave it a 3,000 to 5,000 foot altitude advantage over German fighters. This might seem modest, but in practical terms, it meant P-47s could always position themselves above German fighters, controlling the engagement. Soviet test pilot reports on the P-47D, conducted by the Flight Research Institute in 1944, provide an interesting perspective. The Soviets, who received some P-47s under Lend-Lease, generally preferred their own fighters for the low-altitude combat typical of the Eastern Front. However, their technical analysis acknowledged the P-47's exceptional high-altitude performance, noting that it was unmatched by any Soviet or German type above 30,000 feet. Evolution and improvement. The range problem. By mid-1943, the P-47's high-altitude capability was proven, but a critical limitation remained: range. The strategic bombing campaign against Germany required escort fighters that could accompany bombers deep into German territory. Early P-47 models, with a combat radius of only 200 to 230 miles, couldn't provide protection beyond the German border. This range limitation wasn't primarily due to fuel capacity. The P-47 carried 305 gallons internally, more than most fighters. The problem was fuel consumption. The massive R-2800 engine, even when operated efficiently, consumed fuel at prodigious rates. At high power settings necessary for combat operations, fuel consumption could exceed 300 gallons per hour. The solution came through multiple improvements. First, Republic Aviation developed provisions for external fuel tanks, drop tanks that could be jettisoned when empty or when entering combat. The P-47D5, introduced in late 1943, could carry a 200-gallon belly tank, and later versions could carry 250-gallon wing tanks, plus a 108-gallon belly tank. These external tanks dramatically extended range. A P-47D with full external tanks could fly over 1,000 miles, providing a combat radius approaching 450 miles. This was sufficient to escort bombers to targets in central Germany. Berlin itself was within range. Second, pilots and squadron operations officers developed more efficient cruise procedures. By carefully managing power settings, using optimal cruise altitudes, and employing fuel mixture controls properly, pilots could significantly extend range. These procedures were formalized in pilot handbooks and training programs. Third, the R-2800 engine itself was improved. Later variants incorporated more efficient fuel delivery systems and improved internal components that reduced fuel consumption while maintaining or improving power output. The P-47D, definitive version. The P-47D, which entered service in early 1943, became the definitive Thunderbolt variant. Over 12,000 P-47Ds were built, more than any other P-47 model, and numerous subvariants incorporated progressive improvements. Early P-47D models, D1 through D10, featured the original Razorback fuselage, with a raised spine running from the cockpit to the tail. This design provided structural strength but limited rearward visibility, a significant disadvantage in combat, where situational awareness was critical. The P-47D-25, introduced in mid-1944, featured a revolutionary change: the bubble canopy. This clear, teardrop-shaped canopy provided 360-degree visibility, eliminating the blind spots that had plagued earlier models. The bubble canopy required redesigning the rear fuselage, cutting down the raised spine, and strengthening the structure through other means. The result was one of the most recognizable fighter profiles of World War II. Pilots universally praised the bubble canopy. Combat reports from late 1944 and 1945 show a marked decrease in losses to attacks from behind. Pilots could now see threats approaching from any direction and react accordingly. Other improvements came steadily. The P-47D-28 introduced water injection for the R-2800 engine. This system injected a water-methanol mixture into the engine during high-power operations, cooling the intake charge and allowing higher boost pressures without detonation. Water injection provided an emergency power boost, increasing output to 2,300 horsepower for short periods, critical during combat emergencies. Later P-47D variants featured improved armor protection, upgraded radio equipment, and enhanced electrical systems. Underwing hardpoints allowed the P-47 to carry bombs or rockets, transforming it from purely a fighter into a capable fighter-bomber. The paddle blade propeller. One of the most visible and significant improvements to late-model P-47s was the paddle blade propeller. Earlier P-47s used conventional Curtiss electric propellers with narrow blades. These propellers were efficient at high speeds, but struggled to convert the R-2800's tremendous power into thrust, especially during takeoff and climb. The paddle blade propeller, developed by Curtiss in 1944, featured wider blade tips that increased blade area significantly. This design allowed the propeller to absorb and convert more power into thrust, particularly at lower speeds. The improvement was dramatic. P-47s equipped with paddle blade propellers showed markedly better takeoff performance, with shorter takeoff runs and faster acceleration. Rate of climb improved by approximately 10 to 15%, particularly at lower altitudes where the extra thrust was most beneficial. The paddle blade propeller also improved the P-47's performance in combat. The enhanced low-speed thrust improved acceleration out of tight turns and made zoom climbs more effective. Pilots who transitioned from narrow blade to paddle blade equipped P-47s reported the aircraft felt noticeably more powerful and responsive. High-altitude operations, the daily reality. By 1944, P-47 operations had matured into routine, though routine at 30,000 feet over enemy territory remained anything but safe or comfortable. A typical bomber escort mission illustrates the demands placed on aircraft and pilots. Missions began with extensive briefings. Pilots received information on the bomber formation they would escort, expected enemy opposition, weather conditions, and tactical plans. They studied maps showing the route into Germany, identifying landmarks for navigation, and noting flak concentrations around major cities. Pre-flight inspections were thorough. Ground crews checked every system, paying particular attention to the turbo-supercharger. Oil levels were verified, oxygen systems tested, guns loaded and charged. Each P-47 received approximately 300 gallons of fuel internally, plus whatever external tanks the mission profile required. Takeoff was always exciting in a fully loaded P-47. The aircraft might weigh 17,000 pounds or more with full fuel and ammunition. Pilots advanced the throttle steadily, feeling the R-2800 build power. The P-47 accelerated ploddingly at first, consuming thousands of feet of runway before the tail came up. Finally, at 110 to 120 miles per hour, the aircraft would lift off, and pilots immediately raised the landing gear. Climb to altitude took 30 to 40 minutes and required careful power management. Pilots monitored cylinder head temperatures, manifold pressure, and turbine RPM continuously. Climbing too fast could overheat the engine. Climbing too slowly wasted fuel. The optimal climb profile balanced these factors, typically using 40 to 42 inches of manifold pressure and 2,300 RPM. As altitude increased, pilots adjusted the turbo-supercharger controls to maintain manifold pressure. The automatic regulator handled most adjustments, but pilots had to monitor its operation and occasionally intervene manually. They also had to manage carburetor heat and intercooler temperature, ensuring neither icing nor overheating occurred. Crossing the English Channel and entering enemy airspace, pilots switched their fuel systems from external to internal tanks. External tanks would be dropped before combat, and pilots wanted to burn their external fuel first. They armed their guns, checked gun sight settings, and increased situational awareness, scanning constantly for enemy fighters. At escort altitude, typically 28,000 to 32,000 feet, the temperature was brutally cold, often -40 to -60 degrees Fahrenheit. Despite cockpit heating systems, pilots wore heavy flight suits, gloves, and boots. The thin air required 100% oxygen, delivered through masks that frosted with each breath. The combination of cold and oxygen mask made communication difficult. Radio calls had to be clear and concise. Combat, when it came, was typically brief and violent. German fighters would appear suddenly, dark specks growing rapidly larger. The P-47 formation would respond according to practiced tactics, flights separating to engage different enemy groups. Individual dogfights were measured in seconds or minutes. Pilots who survived often couldn't accurately describe the engagement. Events happened too fast for conscious processing. After combat, the long flight home began. Pilots checked fuel status anxiously, combat maneuvering consumed fuel rapidly, and running dry over the North Sea meant certain death. They monitored engine instruments for signs of battle damage. They helped wounded comrades navigate homeward, sometimes escorting badly damaged aircraft that limped towards England, trailing smoke or fuel. Landing a battle-damaged P-47 required skill and nerve. Damaged control surfaces, leaking hydraulics, or wounded pilots turned routine landings into emergencies. Yet the P-47's rugged construction and stable handling characteristics brought countless pilots home who would have been lost in more fragile aircraft. The killer at low altitude, fighter-bomber role. While the P-47's high-altitude capability remained its defining characteristic, by 1944 it had found another role, ground attack. The same strength that allowed it to withstand battle damage at altitude made it nearly invulnerable to ground fire. The same powerful engine that enabled high-altitude performance could carry heavy ordnance loads. P-47s began carrying bombs, typically two 500-pound bombs.
The men who flew them. Training the Thunderbolt pilots. Converting pilots to the P-47 required extensive training. The aircraft's complexity, size, and unique characteristics demanded respect and understanding. Training programs evolved throughout the war, incorporating lessons learned from combat experience. Initial transition training focused on basic handling. Pilots accustomed to lighter fighters had to adjust to the P-47's heavier controls and higher landing speeds. Instructors emphasized the importance of speed control. The P-47 required higher approach speeds than most fighters, typically 130 to 140 miles per hour on final approach. Too slow, and the heavy fighter would stall uncontrollably. Too fast, and it would float down the runway, potentially running off the end. Ground handling required attention. The P-47's powerful engine produced significant torque, which wanted to pull the aircraft left during takeoff roll. Pilots had to apply right rudder aggressively to maintain directional control. The long nose limited forward visibility on the ground, requiring S-turns while taxiing to see ahead. Turbo-supercharger management was a critical training element. Pilots learned the relationship between throttle, manifold pressure, and turbine RPM. They practiced recognizing and responding to overboost conditions, turbine overspeed, and intercooler icing. They learned optimal power settings for various flight regimes, cruise, climb, combat, and how to manage fuel consumption to maximize range. High-altitude operations training was essential. Pilots flew to extreme altitudes, experiencing the thin air, bitter cold, and operational challenges firsthand. They learned to recognize hypoxia symptoms, the insidious oxygen starvation that could impair judgment and cause unconsciousness. They practice emergency procedures, engine failures at altitude, turbo-supercharger malfunctions, oxygen system failures. Gunnery training emphasized the P-47's weapons. The 8.5 caliber machine guns were powerful, but required proper harmonization, adjusting each gun's aim point so all rounds converged at a specific distance. Pilots practiced air-to-air gunnery against towed targets, learning to estimate range and lead moving targets. They practiced deflection shooting, the difficult art of firing at crossing targets where correct lead angle meant the difference between hits and misses. Combat tactics training brought everything together. Pilots practiced formation flying, the fundamental skill that allowed fighters to work together. They learned tactical formations, optimized for mutual support and situational awareness. They practiced bounce attacks, diving from altitude to simulate combat engagements. They flew dissimilar aircraft combat, testing their skills against aircraft with different performance characteristics. Aces and their stories. The P-47 produced many aces, pilots credited with 5 or more aerial victories. Their stories illuminate both the aircraft's capabilities and the human factors that determine success in combat. Francis Gaby Gabreski became the top P-47 ace in Europe, credited with 28 aerial victories. Gabreski exemplified the disciplined, tactical approach that maximized the P-47's strengths. He emphasized altitude advantage, careful positioning, and aggressive but controlled attacks. His philosophy was simple: fight on your terms, not the enemy's. Gabreski's typical engagement began at high altitude, scanning constantly for enemy aircraft. Upon spotting targets, usually German fighters climbing to attack bombers, he would position his flight for an optimal bounce. The attack itself was calculated violence: a high-speed dive, brief firing pass at close range, and immediate zoom climb back to altitude. Robert S. Johnson, another 56 Fighter Group ace with 27 victories, had a different style. Johnson was more aggressive, willing to engage in extended combat and pursue enemies more persistently. His P-47, bearing the name All Hell, became one of the most photographed fighters of the war. Johnson's combat philosophy emphasized the P-47's durability. He knew he could take hits and survive, which gave him confidence to press attacks. On multiple occasions, Johnson returned with badly damaged aircraft, holes in wings, damaged engines, shattered cockpits, yet always made it home. This durability allowed aggressive tactics that might have been suicidal in less robust aircraft. Walker Bud Mahurin, credited with 24 victories in Europe and later additional victories in Korea, was known for his analytical approach. Mahurin studied German tactics, aircraft capabilities, and operational patterns. He used this knowledge to predict where enemy aircraft would be and position his flights accordingly. He pioneered specific tactics for engaging different German aircraft types. Against Bf-109s, he emphasized high-speed attacks that prevented the 109's superior maneuverability from becoming a factor. Against FW-190s, he targeted them during their attacks on bombers, when they were committed to their attack runs and vulnerable to bounce attacks from above. In the Pacific, Neil Kirby became the top P-47 ace with 22 victories. Kirby's tactics adapted the boom and zoom approach to Pacific conditions. He emphasized energy management, maintaining high speed to enable rapid attacks and escapes. Against the maneuverable but slower Japanese fighters, speed was life. The human cost. For all the P-47's capabilities and the skill of its pilots, combat was lethal. 8th Fighter Command records document hundreds of P-47s lost to combat and operational causes. Behind each lost aircraft was a pilot, dead, captured, or, if fortunate, evading capture and returning to Allied lines. Combat losses occurred through various mechanisms. German fighters, despite their disadvantages, were still deadly. A moment's inattention, an equipment failure at the wrong time, or simple bad luck could prove fatal. Flak claimed many P-47s, particularly during ground attack missions where aircraft flew through curtains of exploding steel. Operational losses, accidents not involving enemy action, took a steady toll. Engine failures, weather-related accidents, pilot error, and mechanical problems claimed aircraft and lives. High-altitude operations were inherently dangerous. Oxygen system failures, cold-related equipment malfunctions, and physiological stresses created constant hazards. The psychological stress on pilots was immense. Combat missions meant hours at high altitude, in bitter cold, constant vigilance for enemy fighters, and violent combat that produced adrenaline surges followed by exhaustion. Pilots flew missions repeatedly, watching friends die, knowing each mission might be their last. The P-47's durability provided some psychological comfort. Pilots knew their aircraft could protect them, absorb damage, and bring them home. This confidence translated to better performance and, paradoxically, to survival. Pilots who trusted their aircraft flew more effectively, made better decisions, and survived longer.
Impact and legacy. Strategic impact on the air war. The P-47's contribution to Allied victory in the air war over Europe was profound, By late 1943 and through 1944, P-47s provided the bulk of fighter escort for American bomber formations penetrating deep into Germany. This escort was critical to the strategic bombing campaign's success. Before effective fighter escort became available, American bomber losses were unsustainably high. The infamous Schweinfurt-Regensburg raids of August 1943 saw 60 bombers lost out of 376 dispatched, a 16% loss rate that couldn't be sustained. German fighter attacks were devastating, and unescorted bombers were vulnerable despite their defensive armament. The arrival of long-range P-47s with external tanks changed the equation. German fighters now had to fight through P-47 escorts to reach the bombers, and this typically proved costly. The P-47's high-altitude capability meant German fighters couldn't avoid combat by climbing. P-47s could follow and usually held the altitude advantage. USAAF Statistical Digest data from 1945 shows the impact quantitatively. In the first half of 1943, bomber loss rates averaged 4 to 5% per mission when penetrating deep into Germany. By mid-1944, with comprehensive P-47 escort available, loss rates dropped below 2%. This reduction enabled the strategic bombing campaign to continue and intensify, ultimately crippling German war production and infrastructure. The P-47's fighter-bomber capability added another dimension to its strategic impact. By 1944, P-47s were ranging across occupied Europe, attacking ground targets systematically. Transportation networks, particularly railroads, were devastated. German military movements became hazardous in daylight. Vehicles caught on roads by P-47s rarely survived. This ground attack capability contributed significantly to the success of D-Day and the subsequent Normandy campaign. P-47s provided close air support for advancing Allied forces, attacked German reinforcements attempting to reach the front, and interdicted supply lines. German commanders reported that Allied air superiority, to which P-47s contributed substantially, was perhaps the most significant factor limiting their operational effectiveness. Technological legacy. The P-47 represented a technological watershed in several areas. Its successful integration of turbo-supercharger technology demonstrated that complex, high-performance systems could be made reliable enough for frontline combat operations. This success influenced post-war aircraft design significantly. The turbo-supercharger technology developed for the P-47 found applications beyond aviation. Industrial turbines, power generation systems, and eventually automotive turbochargers all benefited from developments pioneered in programs like the P-47. The R-2800 engine itself had a remarkable career. Beyond the P-47, it powered numerous other aircraft, including the F-4U Corsair, the C-46 Commando Transport, and various post-war types. Variants of the R-2800 remained in production into the 1950s, and some R-2800-powered aircraft remained in commercial service into the 1990s, a testament to the engine's fundamental soundness. The P-47's structural design principles, building for strength and damage tolerance rather than minimum weight, influenced post-war fighter design. While the jet age would bring different priorities, the lessons about durability and survivability remained relevant. Aircraft designers learned that bringing pilots home was worth some performance penalty. Comparative assessment. How did it really stack up? With the benefit of hindsight and comprehensive data, how did the P-47 compare to its contemporaries? The question is complex because different aircraft excelled in different regimes and roles. Against German fighters, the P-47's record speaks clearly. In air-to-air combat, P-47 pilots claimed approximately 3,700 German aircraft destroyed. While victory claims are always somewhat inflated, combat conditions make accurate assessment difficult. Even conservative analysis suggests P-47s destroyed at least 2,500 German aircraft in air combat. Against this, approximately 750 P-47s were lost to German fighters. This kill-to-loss ratio of roughly 3 to 1 or better demonstrates clear superiority, but with important caveats. The P-47 fought primarily over occupied territory, meaning lost German pilots were captured or killed, while lost American pilots sometimes evaded and returned. The P-47 benefited from superior American training, better tactical doctrine development, and numerical superiority by 1944.
Performance comparisons against specific types reveal nuances. The Bf-109 G6, Germany's primary fighter from 1943 to 1944, could outturn the P-47 at low speeds and low altitudes. In a traditional dogfight below 20,000 feet, a skilled 109 pilot had advantages. But the P-47 was faster, especially at high altitude, and could dive away from any disadvantageous position. The Focke-Wulf FW-190A series posed a different challenge. The 190 had excellent roll rate and good speed at low altitude, making it dangerous in certain tactical situations. But again, the P-47's high-altitude performance was superior, and its diving speed advantage was even more pronounced against the 190 than the 109. The Focke-Wulf Ta-52H, Germany's ultimate high-altitude fighter, actually could match or exceed the P-47's altitude capability. The Ta-52H could reach 48,000 feet and maintain excellent performance at extreme altitudes. However, only a few hundred were built, and they entered service too late to affect the war's outcome. In the few encounters between P-47s and Ta-52s, neither aircraft showed overwhelming superiority. They were roughly matched at high altitude. Against Japanese fighters, the comparison is starker. Japanese aircraft emphasized maneuverability at the expense of almost everything else. In a pure turning fight, a Zero or Oscar would outturn a P-47 effortlessly. But P-47 pilots who followed doctrine and maintained speed and altitude advantage were nearly invulnerable while remaining deadly to Japanese fighters. Compared to Allied fighters, the P-47 was more specialized. The Spitfire was more maneuverable and better suited to combat below 25,000 feet. The P-51 Mustang, introduced to escort duty in late 1943, had superior range and was perhaps slightly better overall at medium altitudes. But above 30,000 feet, the P-47 reigned supreme. Production numbers and variants. Total P-47 production reached 15,683 aircraft, a massive production run that reflected both the aircraft's success and American industrial capacity. This made it one of the most produced fighter aircraft of World War II. Production broke down approximately as follows: P-47B, 171 aircraft; P-47C, 602 aircraft; P-47D, 12,602 aircraft; P-47G, 354 aircraft, built by Curtiss; P-47M, 130 aircraft; P-47N, 1,816 aircraft. The P-47M deserves special mention. This variant, introduced in late 1944, was optimized to intercept German V-1 flying bombs and high-speed reconnaissance aircraft. It featured the R2800-57C engine with improved water injection, producing 2,800 horsepower for short periods. Top speed exceeded 470 miles per hour, making it one of the fastest piston engine fighters of the war. The P-47N was designed for Pacific operations, with extended range and improved high-altitude capability. It featured larger internal fuel capacity, squared-off wingtips that increased wing area, and other refinements. The P-47N could fly over 2,000 miles with external tanks, giving it the range to escort B-29 bombers on missions against Japan. Post-war service. The P-47's career didn't end with World War II. Many nations operated P-47s post-war, and the type saw combat in several conflicts. The U.S. Air Force, created in 1947 from the Army Air Forces, retained P-47s in service until 1949, when jets increasingly replaced piston-engine fighters. Many P-47s were transferred to Air National Guard units, where they served until the early 1950s. The final U.S. military P-47 flight occurred in 1955. Numerous Allied nations received P-47s through military aid programs. The French Air Force operated P-47s in Indochina in the late 1940s and early 1950s, using them for ground attack against Viet Minh forces. The Brazilian Air Force flew P-47s until 1954. The Peruvian Air Force operated P-47s until 1966, the last military P-47s in service anywhere. Several South American air forces used P-47s and occasionally fought with them. Border conflicts between Ecuador and Peru in the 1950s saw P-47s in combat. While details are sketchy, these were likely the last times P-47s engaged in air-to-air combat. The P-47 influenced early jet fighter design in subtle ways. The Republic F-84 Thunderjet, introduced in 1947, was sometimes called the son of the Thunderbolt. While a completely different aircraft powered by a jet engine, it embodied similar design philosophy: rugged construction, heavy armament, and capability to absorb battle damage. The F-84's success in the Korean War validated approaches pioneered in the P-47. Preservation and remembrance. Today, the P-47's legacy lives on through preserved examples and commemorative activities. Approximately 40 P-47s survive in museums worldwide, with several maintained in flying condition. The most famous flying P-47 is likely Snafu, maintained by the Commemorative Air Force. This P-47 appears at air shows across the United States, providing modern audiences a visceral connection to World War II aviation history. The sound of an R-2800 engine